Hello, everybody. We are starting with our first webinar, the first webinar of the ETIN task force. I think that we have to wait just a few minutes for having more people online. We had a lot of registrations, so I think that this webinar will be really interesting for a lot of people. I will start by very briefly introducing myself. I'm Nikolai Gabrovsky. I'm a neurosurgeon from Sofia, Bulgaria. I work in Pirogov, University Hospital Pirogov. As you probably have heard, at the end of last year, the European Association of Neurosurgical Society has decided to establish a new task force. This task force was mainly dedicated to emerging technologies and some innovations in neurosurgery, ETIN task force. As you know, the task force is one of the main instruments of the European Association of Neurosurgical Society to focus on certain topics that are important for the community. And we have been very glad that innovations and emerging technologies has become such a focus and such an important topic for the European Association. The founding member of this task force have been 5 people. These are Enrico Tessitori, Nicolas Sampron, Marcel Ivanov, and Florian Ringel. I will give them to say a few words in a moment. But before all, because the main reason for establishing this task force is the board of the European Association of Neurosurgical Societies, I'm very glad and very thankful that the president of the ENS, Dr. Andreas Demetriades, is amongst us. And I will be thankful for if he say a few words and he give a small welcome address. Andreas?
Thank you, Nikolai. So good afternoon and good evening to everybody. It's an absolute pleasure on behalf of the ENS board and myself personally to congratulate, first of all, the founding members of the new task force for the ENS, and of course to welcome all the participants. We've had more than 360 registrations for this webinar, which clearly shows that there is a lot of appropriate appetite for the topic. Our specialty is very much aligned with emerging technologies and innovation, and therefore this new task force will hopefully engage and inspire a lot of us in the future, and we look forward to more activities, more educational platforms, and in fact more innovations. So thank you to all of the founding members, and just to explain that the board is happy to accept proposals and suggestions, and we do our best to facilitate as much as we can. But I'm looking forward to this. So thank you again, Nikolai, for organizing it, and thank you and welcome to our guest, Professor Kasabov. Enjoy the evening, everyone.
Thank you very much. Thank you, Andreas. Yeah, it's absolutely right that one of the main purposes of this task force is to bring on the same table people from different area of knowledge. And we want to bring on the same table neurosurgeons, engineers, scientists, people that are familiar with artificial intelligence, virtual reality. And this is one of the reasons why our first guest is Professor Kasabov, and the topic will be neuroinformatics, neural networks, neurocomputers, and some application in neurosurgery. But before starting with the speech of Professor Kasabov, I would like to ask some of the founding members of the ETIN why they decided to become part of this initiative. Enrico, probably you first.
Hello, everybody.
Present yourself.
Hello, thanks a lot, Nikolai. And I'm Enrico Tessitore. I'm a neurosurgeon working at Geneva University Hospital in Switzerland. And I must say, like any neurosurgeon, I've always been very fascinated by technology. And I must say that our profession has dramatically changed in the last decades, forcing us to develop skills going well beyond the surgical procedure itself. And we are often confronted with the use of technological tools that require specific and proper handling. But there is no doubt that this technology has made neurosurgery much safer and more precise. Today, I think that our neurosurgical community needs to engage with other stakeholders in this area. Here is the idea of creating this task force, and which is a unique opportunity for us neurosurgeons, for other specialists in this field, in technological sector, but above all for our patients. So really, I look forward to welcome new participants to the platform and to the task force. And then we created a LinkedIn profile where you can join us. We will share our knowledge, our events on this platform. Thanks to all of you for being with us tonight.
Thank you very much, Enrico. You mentioned something very important regarding that we are looking for broadening of our network outside the Neurosurgical Society. We are inviting also, as I mentioned, engineers, people with completely different profile, but working on innovations that could be useful for neurosurgery, and we will change probably the way we work in neurosurgery tomorrow or the day after tomorrow. So they are all welcome to become part of this group and to give their input for really changing the neurosurgery of tomorrow. And now probably Nicolas, one of the other founding members.
Thank you, Nikolai. It's a great pleasure to be here with you and with all our friends. I'm very happy to be here. And when you came with the idea, you, Nikolai, I don't know if you remember, you came with the idea of finding some sort of organization that covered a place that wasn't covered by any of our other committees and task forces, that was dealing with innovation and new technologies in neurosurgery. I think we are living very special times that are challenging and also amazing. And I think that one of the key of this space is to be open to the possibility to other disciplines to join, for example, engineers and computer scientists, and all people that will make the future of neurosurgery together with us. I think that in this time we should be both open to innovation and also critical, because we owe an everyday responsibility with our patients. We need to be open for innovation, but we also need to provide the safety to critical review all the new technologies to be incorporated. So I'm very happy that we start with this amazing topic, which is maybe a little bit out of the traditional neurosurgical topics, but I think that it will show that really start the way in which this task force is ready to be in. So thank you very much. Very happy to be with you. Very excited too.
Thank you very much. Thank you very much, Nicolas. So I'm really glad, that we are looking exactly different from purely neurosurgical topics, and I hope that it will be really interesting. As I mentioned, there are different ways to join us. The first one that we have established is a group named ETIN in LinkedIn, but we are opening actually new ways for people that want to join via other social networks, and I hope that will become a society of really people with really different type of view over certain problems. Now, before starting giving the floor of our speaker, I would like to say that our first webinar is on the International Women's Day. I suppose that this should be a good sign, and I want to congratulate all of you with this day, because for me, this is, how to say it, actually people that work a lot, giving all from them in our everyday jobs are very important for this seminar, and I want to especially thanks to the ENS office. Really, thank you very much for all your efforts to make this happen. Now a few words about our speaker. I want to present you Professor Kasabov. Professor Kasabov is a Life Fellow of the Institute for Electrical and Electronic Engineers, Fellow of the Royal Society of New Zealand, Fellow of the College of Fellows of International Neural Network Society, and many others. He is founding director of the Knowledge Engineering and Discovery Research Institute, professor of knowledge engineering at Auckland University and Technology. He has published over 700 works, 10 textbooks, 28 patents and authorships and certificates. He has also been included in Stanford University list of top 2% of scientists in the world by citation since 2020. Of course, this is only part of everything that Professor Kasabov has done, so I will ask him to briefly introduce himself. Professor Kasabov.
Thank you, Professor Dabrowski. It is my pleasure to be here, as this is the first seminar on emergent and AI technologies for the area that is very important, neurosurgery, and I will try to be clear about what we can do and what the future will be. My background is I was born in Bulgaria, studied in Bulgaria, and then I worked at the Technical University in Sofia. Now I am a visiting professor at the Bulgarian Academy of Sciences on European projects related to neurosurgery, indeed. And I also worked in the UK in the past. Now I'm in New Zealand, but of course I spent time in Europe, working in Zurich, working with colleagues from Ulster, and keeping in touch with my colleagues all over the world. So it's my pleasure to give this seminar. Of course, it will be a brief introduction of some techniques that we developed in my group. Thank you, Professor Dabrowski.
Thank you very much. By the way, I have to mention that actually you are in New Zealand, so we had to postpone a little bit the starting of our the starting hour of our webinar, because it's early morning in New Zealand actually.
Well, sun is rising now. Sun is rising. It's not too early.
Good morning, Professor Kasabov. And before starting with your speech, I would like to tell to the audience that if they have an important part of these seminars will be the contact with the auditorium. So everyone is everyone can ask a question in the question and answer box, and or eventually in the chat. But the question and answer box is the main way to ask a question. So please use the Q&A box that is on the bottom of your Zoom screen. This is the way where you can ask your questions. So thank you very much. I hope that all the audience will be active and we will have a lot of questions for the interesting topic that Professor Kasabov will present. So Professor Kasabov, please, we can start with your speech.
Can you see the screen now?
No.
Not yet. Okay, so let me just. Okay, you can see the screen now.
Thank you.
Is that okay now? So you can see the screen, you can hear me.
It's perfect. We hear you perfect.
Thank you very much. Well, I would like to say that I decided to accept this invitation by Professor Dabrowski, talking about a little bit more broader view of the technologies. And the technologies start with neuroinformatics, where data comes from, and the artificial intelligence area uses this data to develop techniques like neural networks and towards neurocomputers. And I also agreed to Professor Dabrowski to include some applications in neurosurgery. I was not aware that last year there were 20,000 papers published in AI in neurosurgery. I couldn't go through all of them. I'm sorry about this, but I still managed to capture some ideas, what is there and what needs to be developed in the future. And first of all, congratulations to the group and to the task force that is formed by founders. And I found very what is important in the mission that we can contribute to. The mission says that new emerging technologies and innovations in neurosurgeries are needed. And keywords in this task force are robotics, artificial intelligence, virtual reality, emerging technologies. Of course, it includes also data science. We feel that we can collaborate on these topics. And I will go through some points that will start with why do we need artificial intelligence, and what is neuroinformatics, what is neural networks, and then we will go to some applications in neurosurgery. Some of the points I have made and in details in a book which is called Time, Space, Spiky Neural Networks and Brain-Inspired Artificial Intelligence, published by Springer. I will leave my presentation with Professor Dabrowski and the office of the task force. So anybody who is interested to have the copy of the presentation, they will be very welcome. Talking about artificial intelligence, it actually goes into every area of technology and science, but the most beneficiary area is healthcare, according to the PwC PricewaterhouseCoopers. And healthcare will benefit a lot to several points. One is personalization of healthcare. The other one is data available, time saved, and utility available. So there are many areas in healthcare, and healthcare can support the development of artificial intelligence and can benefit a lot from that. In terms of what kind of artificial intelligence techniques will be more important in the future, and there is also another prediction that the so-called deep learning techniques here will bring more benefit, more revenue to healthcare, along with machine learning, along with computer vision. But deep learning, and deep learning now it means neural networks, neurocomputers, and that is what I want to talk about. If we look at some publications in AI neurosurgery, I looked at a few of them. Of course, there are problems in neurosurgery that can benefit from artificial intelligence, operative work, healthcare access, surgical procedures, post-operative follow-up research, and I have copied this from a publication by Mohammad Mofateh from Oxford University. And if we look at the publications in this area, we can see that in 2020, there were more than 20,000 publications, and cumulatively 70,000 publications that in neurosurgery, they mention artificial intelligence, machine learning. So it's something that we can address in the future. And several papers that are in neurosurgery papers commented on the benefits of artificial intelligence and also on the problems. One of the benefits, of course, is that AI techniques may permit rapid and detailed analysis of the large quantities of clinical data, talking about diagnostics, decision-making, prognostics. But there's some also perils. For example, faulty, inadequately trained or poorly understood algorithms may produce erroneous results which may have wide-scale impact. We have to be careful how to use artificial intelligence. And one of the papers published also recently has the following motto: create a model that is as sophisticated as the problem requires, but not more so. We have to be careful not to overdo this as well. So not too simple models, but not too complex models that can be developed to serve the purpose. And talking about neuroinformatics is the area where data is collected. And in neuroscience and neurological data is plenty different types of data. We talk about DTI, we talk about fMRI, we talk about EEG data, we talk about brain scans. So how do we deal with this enormous amount of data to create a model that can help people understand and use these models in practice? Neuroinformatics has challenges such as we need to look at improved quality of data, multiple modality. How do we put so many modalities together for a better diagnosis and prognosis? Different types of data. We have vector-based, we have longitudinal data over time. Efficient learning from data, adaptive, predictive, personalized modeling. This is, of course, a key issue now to have a personalized models for everybody, other than one model for everybody in the world. In explainability, no more boxes. Please, as we say, let's have our systems to explain what they have done and how they have done that, so we can understand better what is the issue. And of course, neural networks are one of the techniques, only one technique that can help in this respect. Neural networks are inspired by some principles of the human brain with long history from 43 to now. And neural networks are computational models that can take input data and they produce an output. And the type of neurons that we use in neural networks can vary from very kind of not so adequate to brain data and more adequate to brain data. And this is also a development in neural networks from the first generation of Rosenblatt to the second generation of the multi-layer perceptron, and now to the third generation of spiking neural networks. But early neural networks, they had no adaptability, no explainability. They were black box. They were criticized a lot. And that is why we needed to develop new techniques that would be more appropriate for the data. And new techniques were also inspired by the human brain. For example, the early deep neural networks developed by Fukushima were inspired by the visual cortex, how the visual cortex recognizes objects. Deep convolutional neural networks are now the state of the art. And deep convolutional neural networks means that we have many layers of neurons that take an image and recognize the image. Unfortunately, the current deep neural networks are excellent for vector frame-based data. This is fortunate, of course. Not so for spatial temporal data and computer vision for video data. There is no kind of asynchronous events learned in the model, difficult to adapt to new data, and the structure is not explainable. So explainability is very important to have in the computational models, and there were some models that were developed to explain to explain what they have done, how they have done from the data, and to extract the essence of the data in terms of rules. And these are the so-called fuzzy neural networks. Some of them are well developed, well used in practice. So we can say that knowledge can be extracted from data rather than having a black box now. Talking about also inspiration from the brain as the new generation of the computational intelligence, of artificial intelligence, Yeah, we the scientists, we look at the human brain as the most sophisticated product of the evolution. It's a lifelong learning system for knowledge representation and knowledge transfer. And we talk about different types of memory, short-term, long-term, genetic, different types of data, different scales of data processes, nanoseconds, milliseconds, minutes, hours, many years. And knowledge is represented as deep spatial temporal pattern that evolve, adapt over time. For example, this is the pattern when a person sees an object with the visual cortex activation, and then the person is grasping the object with the activity of the motor cortex. Maybe the person can have a cup of coffee as well. Anyway, so the challenge is for artificial intelligence is how do we adopt, how do we adopt some principles from the human brain, develop better artificial intelligence systems so they can serve better the clinicians, the practice in health, and in neurosurgery in particular. One development, recent development, is called spiky neural networks, and spiky neural networks use a different type of information than traditional neural networks are using scalars or numbers. Spiky neural networks represent information as binary unit spikes over time. So time is represented in the data, in the model, and time is definitely, and space is represented in the brain functions. So if we don't have time, we may not be able to understand what the model does over time as a dynamic model. So spiking neural networks, this is a neuron, spiking neuron that takes inputs as spikes, trains to be activated when a threshold is reached and to emit a spike. Spiking neural networks has been developed in the last 15 years or so, different types of spiking neural networks. And the beauty of them is that they can represent spatial temporal data, and they can think higher level function like frequency, like rate, to low level genetics. And they have also inspired the development of brain-inspired computation algorithms and the creation of neurocomputers. And talking about brain modeling and brain-inspired systems, we should make a difference. There are brain modeling systems that are focused on detailed analysis of brain functions and their computational modeling, like the Horizon Blue Brain project and the virtual brain, which is a very, very strong project, very strong research. But the other side is brain-inspired data analytics, using brain principles to build models of brain data that can be used to understand brain functions. And this is the so-called reverse engineering approach. And I will talk about this reverse engineering approach more specifically as one system developed in my group, and this system is called NewCube. And NewCube is a three-dimensional structure that uses a brain template to allocate neurons representing different brain areas. So we can make a brain template in this cube and this model. And in this case, we can learn, this model can learn from the data that is available, including genetic data or temporal data, of course, and spatial temporal data. And this model can be analyzed to produce an output like predicting signals, brain signals, or classification of brain states. There are different stages in the development of such models that are based on spiky neural networks. One stage is how do we encode continuous value data into spikes, and there are some principles used as from silicon retina as a threshold-based in Zurich in the Institute for Neuroinformatics, or cochlea-based information data that is a continuous data encoded into spikes using the so-called cochleograms. Once data is encoded, it can be used in to train spiking neurons in spiking neural networks, and we can use different types of such spiking neurons. how do we train a system using spiking neurons? One of the methods is called spike time dependent plasticity. And definitely, this is the extension of the Hebbian learning rule in neural networks. And the extension is with the inclusion of time. So time is important when one neuron spikes and another one spikes after that. That is a long-term potentiation. If that happens many times, that may show some causality. Otherwise, it is long-term depression. So time is learned in spiking neural networks to change the efficacy of the connection weights. And that is a significant departure from traditional neural networks like multi-layer perceptron. And some of the papers in neurosurgery, AI neurosurgery, they said, well, our models are not good enough. And I should say that they haven't been developed for you to use in situation where you have spatial temporal data. They have been developed for some other statistical methods. So we have to look at new methods. And spiking neural networks can also be trained in the so-called supervised learning mode to react, to emit an output signal when particular pattern is presented. That is called supervised learning. So we can make a neuron spike earlier the way we perceive objects and we react to avoid collision or to avoid some unfortunate situations. We predict the output of our neurons, and the neurons predict their signals and they can react accordingly. This new system is trained from data, as I said, sequence of 5 sequences after encoding of the data, and this data is entered into spatially located neurons, and learning in the tube is spike time dependent plasticity, creating connections, changing connections, so that's a pattern is formed from the data, and this pattern is recognized in certain output. And here's one video. Can you see the video, please? So you can see the video. So that is how the system evolves over time. And if we have this simulator, and we do have this simulator, we can observe what areas is more connected, means that more data is coming. It could be EEG data, it could be fMRI, changing the connection weight, so we can observe that. This is not a black box anymore. And examples could be from different EEG data that we have continuous training of this tube over time, and the tube develops its connections. And most importantly, we can trace the activity of this tube when the new data is entered, similar to what I showed, how the brain learns to create a trajectory of when the person is seeing an object and grasping an object. So we can explain the patterns in this model that reflect the patterns of activity, the data, back to the human brain as a reverse engineering. We can extract important dynamic information. Dynamic information means that how many times certain areas of the brain represented by these channels, if you like, the channels, how much they exchange information between those spikes here. And this dynamic model will tell us what are the important areas of represented in the data that are more important for this state of the brain. So this is no more a black box. We can extract information. We can extract rules saying if this area is activated first, and then this area, another area is activated second, etc. And this is the output that is recorded. And we can understand why this output, or could be state, or could be classificational, why this output was presented. And based on these algorithms, my group has developed one environment that can be used and that can be downloaded free. It's called NeuroCube, and here's the website. So this environment can be used to develop applications, different applications on brain data and other spatial temporal data using some of the so-called neurocomputers, or not using neurocomputers, because we can say that such spiking neural networks 10-bit systems, once developed as a model, once proved and validated, can be implemented on a von Neumann architecture. This is John von Neumann, and the first digital computer was developed by Jonathan Nassau. Or its algorithms can be implemented on neuromorphic computers, where instead of bits, neuromorphic computers use bits at times, so bytes, or quantum computers where the computers use the so-called qubits rather than bits or bytes. And the hardware systems or neurocomputers are being developed very, very intensively. Started from Carver Mead in '89, and now we have the Spinnaker system in Manchester, led by Steve Furber. We have chips, spiking neural network chips by Giacomo Indiveri in Zurich and Toby Delbruck at the True North by Dharmendra Moder in IBM, and the new one, which is called Lohia by Intel. Now, talk about applications. We can look at different applications of such techniques, some of them very much relevant to neurosurgery. And talking about brain data, we can use fMRI data, EEG data, and I'll show some examples of how that can be done using steps of encoding information, learning this information, encode it into a model properly created, and then analyzing this model in terms of activities to go back to understanding what the brain is doing, and that is the reverse engineering I'm talking about. One particular application is called brain-machine interfaces. Brain-machine interfaces are when people use their brain signals to control some robots. And he is one of my students, Stefan Phillips from Germany, who controlled this robot to move with his brain signals. Of course, we need a system that hears the signals from Stefan and emits signals to control the robot. And we can also talk about the grasp and lift, the kind of task. We can follow what the model has learned from the data, and we can compare the activities of the different areas of the model. We can compare it with the information, the knowledge, how people do that from neuroscience, and we can see that rules can be extracted from this model to tell us what the person is doing. And this is also published as a neurorehabilitation method in scientific reports, where we have EEG data collected, we have model created all the time, and then it's an imaginary movement of prosthetics. One of the projects that I would like to mention here is in brain-machine interfaces is a project that was funded by the European Union, European Commission, and it is called NEMO BMI, Neuromorphics BMI, and it is from the Horizon Europe, with the participation of colleagues from France, CEA, Grenoble, the Netherlands, a company very important research in neurorehabilitation called Onward, Switzerland, EPFL, and Bulgaria, Institute for Information and Communication Technologies. And this is our job here. The main purpose is to decode signals from the brain and use these signals to move prosthesis and to recover damaged brain nerves. And this is brain nerves in spinal cord that could be recovered based on brain signals. This is just a starting point. And here's our team in the Institute for Information Communication Technologies in Bulgaria, with a co-lead by Professor Kuprinkova. And I would like to say to everybody who is participating in this seminar, every woman congratulations with the 8th of March, the International Women's Day. And it is very important to have our colleagues to join us and to work with us. Thank you. In virtual reality, we can observe how people, when they recover from stroke through the virtual reality artificial hands movement of the virtual hand, we can see. We can also measure how the brain is working, how the brain is improving, what part of the brain is developing in an online mode. We can also observe how people control objects or how people navigate, and we can understand better what they do. Of course, there's also some interesting research that we have done with a group from University of Ottawa called Cyber Sickness, and the recent papers in one journal which is called Neuroinformatics, we published research that shows that with 85% accuracy, we can predict whether a person will have a cyber sickness or not, even before they experience this this situation. Only in a resting state, analyzing the brain data can be used to predict whether a person will have a cyber sickness or not. Personalized modeling is something that we developed as in introducing both personal data and dynamic brain data to create a model for a person. And if we create a model for a person, individual, the accuracy of prediction of the outcome is much higher than if we just use one model, a regression, or even a neural network for everybody anywhere in the world. And this personalized modeling is something that we will develop in the future. Personalized modeling is also used in many other applications, like longitudinal MRI data to predict dementia onset of Alzheimer's disease using a large cohort of data and building a model for every person and testing the model on this person. Also publication in neural networks. We can also develop different structures of brain-inspired spiking neural networks that we can structure them according to one personal MRI scan. And we made this model a personalized model. And this personalized model can be used in different applications, like predicting the effect of mindfulness, how mindfulness changes the brain, predicting or classification of some comprehension using fMRI data, or merging fMRI and DTI data together. And that is also very important to develop new methods for integrating space, time, and direction. Predicting stroke occurrence a few hours ahead is also possible using some both personalized and environmental data that trigger the stroke. Using personalized modeling in different areas show much better results than traditional methods like the perpetual machine, multi-layer perceptrons, and this is not incidental because we use spatial temporal data. As discussions, I would say that the approach that we take now with the brain-inspired spiking neural networks developed for particular application tailored has lots of advantages, and I have discussed this in this book, Time, Space, Spiking Neural Network, Brain-Inspired Artificial Intelligence, and also there is quite a lot of discussions on these issues in the so-called Springer Handbook of Bio Neuroinformatics, also published by Springer. Problem is that, of course, we have to deal with lots of parameters. Next stage is to introduce genetic along with neuronal data to work to have a better model for a person, integrating different modalities like fMRI and EEG data that are in different times and spatial scales is important. And I would like to finish my presentation following the instructions by Professor Dabrowski that Of course, we have to be careful with time in the evening time. We have just formed a new group which is called N3EG for Neuroinformatics, Neural Networks, and Neurocomputers. Here is our website, and we have seminars. We will have also some, and we definitely would like to keep it multidisciplinary, where we have people from neuroscience, we have people from computational intelligence, we have people from engineering. So this is very much interdisciplinary group that we have formed, and we will have seminars together for the future. Thank you very much indeed, and I'm happy to take any questions.
Thank you very much, Professor Kasavov. It was a very interesting speech. We had some problems with audio from time to time, but this is another proof that you are talking from very far. But I hope that we could get most of this interesting information. For me, one of the very important messages was that if I had well understood that with this type of neural networks, they do not represent black box anymore. So I think that this was one of the very important concerns regarding neural networks, that we don't know what exactly is happening inside them. So thank you very much for this interesting information. Now, any questions? I have to check our Q&A.
Yeah, Nikolai, I have a couple of questions, if I may.
Please, Nikolai.
So I thank you very much, Professor Kasavov. I enjoy, despite of the low quality of the sound, I enjoy your presentation very much. So I have, first of all, a very simple question, and which is, in which sense the neural network are similar, and in which sense they are different to the real neural network, the wet, the one that we see every day in the operating room?
Yeah. Well, the answer is there is no one neural network, artificial neural networks. There are many types of neural networks that have differences with the real ones to different extents. So we can have neurons that fully imitate biological neurons if we need that. And we have neurons that are more data oriented for capturing data patterns. So I think this is a continuous of, and this from the beginning of the neural network area, and it continues in the future. And we can see that more and more biologically plausible neural models are created. The question is, do we need complexity? We need complexity as much as it serves our models. And if we have data, we have to use the proper neurons and neural types. For example, for temporal data, we can use spiky neural networks much better. But for vector-based data, we can use some multilayer perceptrons still, or deep neural networks with different types of neurons that are not spiking neurons. So I think we have to choose which ones fits better the purpose of the study.
Thank you, Professor. Thank you very much. There is a question that is maybe a little bit specialized for some, but it's regarding what you mentioned about the explanation. I mean, in the neural network, as I understand, is a kind of a box with a very complex computer next that you put it into a big set of data, you feed the network, and you get an outcome.
Yeah.
And what do you really mean with explanation? Are you meaning explanation about things in the real world? For example, we can ask a computer to explain how something works, or you mean it's just explaining what it did to get to the conclusion?
Well, I will go back to Aristotle, from of course, the known philosopher who studied data to extract rules. And some of his rules were not correct. They were updated, of course, later. Now we have tools to take the data, learn from data, and extract some knowledge, extract some rules that can be used by the users. And talking about brain data are, so most of the brain is spatial temporal. If we don't have proper tools, proper methods, AI methods, we won't be able to understand the dynamics of the brain functioning. And that is where spiking neural networks can be used to learn the spatial temporal patterns. And we can extract these patterns, we can visualize them. We can visualize them even in online. We can see how the paralyzed person is learning to move a hand and to move in a space. So we can see that. This is the explanation ability of the neural networks that we would like to, and we are developing. And I am against the black box. And everybody, I would say in the United States and Europe, they say, no more black boxes, please. And this should be the case. Now we have to move to open boxes and understanding from our model what the brain is doing in a so-called reverse engineering. Thank you for the questions. Very much hot topics at the moment. Yes.
Thank you very
we
much.
are really looking forward to understand what is happening in there. And sorry, Nikolai, for I interrupt you.
I ask a question. We are all of us. We are for the last few months talking about ChatGPT. So this is a topic that not simply is promising, but it's really it's really something that has completely changed our view about artificial intelligence, if this is correct to name it like this. And we saw some applications that for a few months has shown results that are not simply impressive, but really will change the day tomorrow. And we will change completely not only the way we interact with the machines, but also a lot of professions will probably disappear or will at least change. What do you think about ChatGPT and such type of artificial intelligence constructs?
Well, if ChatGPT just in one sentence, this is only one system that is a language model, and there will be many more now being developed. And especially in China, we will see several very high tech. ChatGPT is a common use. I wouldn't recommend it for experts because the information ChatGPT uses is generally information available everywhere, not necessarily peer-reviewed for as an expert knowledge. And also the point is that new information can be added by anybody because ChatGPT asks you what is your ideal answer, and you can and people can answer fake information. So ChatGPT is good as a starting point, as a language model. I wouldn't recommend it for experts.
Okay, thank you. But if we look a little bit in the future, the ChatGPT appeared for the general public for a few months. Probably you had knowledge about it for long years, but for the general public, it has become a star, I would say, for a few months. And if things change so fast, what can we expect, let's say, in a few months more, or in a year, or in 2 years? If we have such an exponential growth, what do you think will happen? Do you think that this advice not for professionals will remain relevant for a long time?
Well, I would say that it's good for the public to extend their knowledge, general knowledge, with a careful consideration, because some of this knowledge may be true, may not be true, and it is, of course, if you go to perform an operation, I think you better look at the professional publications and the peer-reviewed publications, and if you want to have new knowledge. But for the general public, it will increase, I think, the IQ of the whole planet, the population in the planet. Definitely, it will improve the IQ of the general public.
Thank you.
Nikolai, we have a question regarding the brain-machine interfaces, if I may. So,
Yeah.
Professor, it's a very promising technology for us that we have to deal, for example, with spinal cord lesions. Usually young patients paralyzed for the rest of their life. With current technology, as it is really a hope for all those patients, and we are waiting a lot from that. So the question is, where is the most challenging problem? Is it the actual brain-machine interface? So how to read the information that the brain is processing? Is it how we do next in the neural network, or is it the connection of that with the effector? Thank you.
Yeah, that's a wonderful question. Let me say that this research question is the main question we have to answer in this project, which is called NEMO BMI. And maybe if I give another seminar in two years' time, I may be able to answer this question because it is the research that we are doing at the moment. But wonderful indeed. Is it the problem in brain signals? Is it the problem in our detecting the brain signals? Is it the problem of control feedback? And how is feedback used to improve this? This is something that we are working on. Thank you for the question.
Okay, so we are close to the end of our first webinar. We don't have time for more questions. Thank you very much, Professor Casabo, for presenting this very interesting lecture and talking about such interesting topics. It was a pleasure for us, and thank you for using a language that was that we, as general public, as neurosurgeons, was comprehensible for us. I think that this is a very important step for us to use this common language that will permit us as neurosurgeons to explain what are our problems and for you as scientists to find a way to resolve them, hopefully. I would like to everyone that has been part of this webinar tonight, to all the founding members that could join, and also for those that couldn't join because they are still working, as I found, as far as I receive some messages. Thanks very much to the Office of the European Association of Neurosurgical Societies that facilitated this process and made it possible. Thank you, Andreas, also for joining. And I hope that this was a very good first step. And now our next webinar will be in 2 months. You will receive additional information. Please be active, join the LinkedIn group, and stay informed. We're going to be informed for the other options for joining the ETIN task force. So I wish you a wonderful evening, and till very, very soon, I hope.
I would say thank you very much, Professor Dabrowski. Thank you, everybody. And I will finish my presentation with apologies that I see 39 questions in the chat room. I was not able to answer these questions. I'm happy if you send these questions to me on the email, and I will have the presentation with Professor Dabrowski as a PDF file. Let's start now to communicate on these issues and addressing these questions that you have, we have in the chat.
Definitely.
Thank you very much. Thank you.
Definitely. Thank you once again. I hope that this was our first meeting. Thank you very much, and good evening to all of you.
All the best. Bye-bye.
Bye-bye.
Bye. All the best.